In this video, we're going to talk about basically finding the inverse of an inverse, i.e., how can we show that an inverse truly undoes its original operation. And as I said to you in the first video, you've actually been doing this for quite a while, where we talk about inverse operations. So, for example, in primary school, you would often think about starting at a number. If I did something to it, say, for example, I multiply by 3, my next number would be 15. The inverse of multiplying by 3 is dividing by 3. So 15 divided by 3 is 5. What we're looking at as we go across this particular row is the fact that after I've done an operation, the inverse goes and undoes the operation. So we end back up at our starting point. We can see this happening again in the next one. 9 plus 7 will be 16. Okay, the opposite of adding 7 or the inverse is subtracting 7. Okay, 16 minus 7 is also 9. Doing this more generally, i.e. for an algebraic statement, for example, if I start with x and I multiply by 5, I end up with 5x. If I take 5x and I divide by 5, I end up with x. All I'm trying to say here in terms of this particular explanation is the fact that the inverse undoes whatever the initial operation is doing, and as a result, we end up back at our original input. Now that's inverse operations. We want to go and put this in the context of extension 1. And instead of just operations, we want to talk about functions. So let's unpack that a little bit, okay? I want you to recall back to composite functions, i.e. anything that was in this form. So it was a function of a function. And inside of that, we had an input function and we had an output function. Okay? So using this idea, you want to ask yourself before we move on, what might this mean if I go and create a set of composite functions where I'm finding the inverse of the original function? What might we end up with? So what we're going to do, okay, is we're going to unpack that algebraically and see if you notice a little bit of a pattern. Okay, so here's the first question. We're going to find the inverse of the following function, and then we're going to go and find inverse so the inverse of f of x, okay? And we might notice something that happens. So you'll notice here in this particular question, it's almost like I've got y equals x plus 3. To go and find my inverse, I'm going to switch the input and output. So I'm going to let x equal y plus 3. Rearranging, I'm going to end up with, okay, I'm going to end up with y is equal to x minus 3, and that is my inverse function there. It is x minus 3, okay? Now, I want to go and find inverse f of x, okay? So I'm going to do a function, the original function inside of the inverse. So I'm going to look here, okay, in terms of the fact that this is going to be my inverse function, this is going to be my output function. So in my inverse function, I'm going to replace wherever I see a x, I'm going to replace it with this entire f of x, okay, which is equal to x plus 3. So you'll notice I've got x minus 3, all right? So wherever I see that x, I'm going to replace it with x plus 3 based on the fact that I'm substituting in a function, okay? So I end up with x plus 3, and then I'm going to subtract 3 off of it. So this is where you see the x, and I've replaced it with the input function there. Okay, and then the minus 3 is coming off the back of that equation. And then simplifying that down, you might notice something interesting happens. Equals x plus 0, which is just x. Interesting. I've started off with just with two different functions, composed them. Admittedly, they're the inverses of each other, and I've ended up at a singular input of x. It's kind of similar as to what actually happened up here. Let's go and test this and see if it holds for another particular example. So I'm going to get you to pause here and have an attempt for f of x equals square root of x. Okay, if not, you're welcome to join me in doing it. Okay, so I'm going to switch my x and y to find my inverse function. So therefore, I'm going to let x equal root y. Okay, now I'm going to square both sides, not square root. Okay, squaring both sides, I'm going to end up with x squared is equal to y. I don't have to worry about the plus or minus here because when I square, it takes care of the negatives for me. So I end up with my inverse function as being my original parabola, okay? Being equal to, okay, x squared. Now let's have a little bit of a look. We're going to do the inverse function, and inside of it, we're going to put the original function. So wherever we go and see an x, okay, we're going to replace it, all right, with our the value of our original function, which is root x. Now, this is what's going to happen. Instead of x squared, it's going to become root x squared. You'll notice that this is going to then become, because the square and square root cancels, just x again. So you might notice a little bit of a pattern happening. When I take my original function and I put it on the inside of my inverse, it undoes everything that the inverse does. Okay? So in summary, right, if we take a function and we apply its inverse, we will always go and get x back. Okay? Basically, it's because the changes that happen from one function is then cancelled out, okay, in the inverse function. So you end up with this really, 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 really neat little formula that the inverse of f of x is equal to f of the inverse of x, which is equal to x. And that's all for this particular video series. Okay? Thank you very much. Hope you found it useful.